This is problem 15.49. It's on page 1017. In the planetary gear system shown, the radius of gears A, B, C, and D is 30 millimeters, and the radius of the outer gear E is 90 millimeters. Knowing that gear E has an angular velocity of 180 RPM clockwise, and that the central gear A has an angular velocity of 240 RPM clockwise, determine A, the angular velocity of each planetary gear, and B, the angular velocity of the spider connecting the planetary gears. Let's make a quick sketch of this. So there's ring gear E. It has angular velocity 180 revolutions per minute. Let's make that something useful. 2 pi radians per revolution, and a minute has 60 seconds. So that gives us an angular speed of 6 pi radians per second, of course clockwise. Right. And of course the gearing, if I can make it kind of to scale, looks something like this, where all these inner gears are the same size, and there's a spider connecting the centers of the gears together to hold them in place. So we've got gear A in the center, gear D down here, gear C here, and gear B up here. They told us the angular speed of A, and that was 240 revolutions per minute. Of course, I converted that as well. Comes out to 8 pi radians per second. And that is, of course, also clockwise. Okay. The radii A, B, C, and D are all the same at 30 millimeter, while the radius of E is 90 millimeter, as it would have to be, obviously. Okay. And I think that's it. So we want to find the angular speed, really, of B, which is going to be the same as C and D. And also, we want to know the angular speed of the spider. So this is just a velocity problem. It's not an acceleration problem. I'm going to define some points. I'm going to call this point 1 and this point 2 just because the letters are already taken as names. And I'd hate to continue with more letters for bodies, since bodies are given letters. And I'd be using letters for points. So we'll use numbers. The velocity of point 1, which is right here, has to be, now let's think about it. We could think about it as velocity on B or velocity on E. Notice those 2 points have to have the same velocity because the gear teeth have to mesh. If the gear teeth don't mesh and they have different velocities, you're going to start stripping gear teeth off. That doesn't work. We're assuming that's not what's happening, right? So E and B must have the same velocity at that point, and it would be off to the right. In fact, let me start to draw it down here. So point 1 would have some velocity off to the right, V1, and we can calculate it based on the angular speed, omega E, of gear E, the outer ring gear, times the radius of that gear. So that would be 6 pi radians per second times a 90 millimeter radius equals 540 pi millimeters per second. Now we can also calculate the speed of, let's see, I did not call this 2, I called it 4. I don't remember why. Let me switch the number. So this point here where B and A mesh, I'm going to call 4. So omega 4, not omega 4, pardon me, V4, we can figure out from the angular speed of A, because we were told how fast A is rotating. And so A has to rotate with some speed, clockwise, right? So this point's going to the right. How fast? I don't know, we'll find out in just a second. There's V4. So omega A times the radius of A. Notice both gear E and gear A have center at the center of A. So 8 pi radians per second is the angular speed of gear A. Multiply that by the radius of A, all have radii of 30 millimeter, and now we know the linear velocity of that point on the top of gear A, 240 pi millimeters per second. So now we know V1 and V4. Well, what would that do for us? Well, there must be a ground pivot somewhere, right? There must be a ground pivot. If you think about it, this point, point 1 and point 4, are also points on body B that have exactly velocity V1, V4. Again, otherwise gear teeth are stripped off. So there must be some point on ground where body B is rotating about. You might say, well, that's easy, that point's right here. No, it's not. If body B were rotating about this point on ground, then this point would be moving to the right, and that would have to move to the left. And that's not the case. Both are moving to the right. Therefore, the motion, the rotational motion and the translational motion together have a center somewhere else, and I will call that center G, let's say 1. And so the distance down to that center, I will call RG1. And hopefully you see the picture now, that this point having zero velocity would make a shape something like this. In other words, as you move farther and farther down on body B, the velocity decreases. This is the point with the minimum velocity, but if we imagine B to extend farther out into the plane, we could continue moving down on that body and eventually find a point where at this instant in time we could pin that point on body B to ground, and that's the point, maybe down here, maybe here. I don't know where it's at. It's on this line somewhere where B is rotating about that point. So, looking at V1 in a different way, more as this triangular setup, well, that would be omega B times RG1, wouldn't it? Similar equations to these, but now we're talking about the velocity on body B at point 1. And so the angular speed of body B would have to be the velocity of point 1 divided by RG1. We don't know where it's at yet, but that's okay. And if we look at V4, that would also be on body B, omega B times what distance? Well, now we just need the distance between this point and this point. So notice that the distance between V1 and V4 is the diameter of the gear. It's 2R, right? So the distance here to here, we would just say is RG1 minus 2R, where R is just the radius. That way we get diameter of gear B. And if you like, you could put a subscript B there. It doesn't matter. There's only one radius in this. Anyway, we call it RA, RB, whatever. They're all the same. So couldn't we then substitute in V1 over RG1 for omega B and find then that V4 is equal to V1 divided by RG1 times RG1 minus 2RB. And we could write this as V1, notice the RG1s would cancel in the first term, minus 2V1 RB over RG1. Now, further, we could say then that V4 over V1 is 1 minus, you know what, I've made a mistake here somewhere. I think I've made a mistake in my solution because when I subtracted the radius, I didn't subtract 2 times the radius. So I'm here working at the board and realized, well, this point is up here and this point is down here. That difference in distance is 2 radii, not a single. In my solution, I forgot that too. So I think I've made a mistake in my solution. I'll have to go through. I may not be able to give you numbers. Let me make sure that I'm not thinking about this wrong. Because my numbers came out and I thought, well, that seems reasonable, because a lot of times when people write these problems, they'll make the numbers come out nice and round. And I got nice round numbers, so I was happy with it. But let's see, V4 would have to be RG1. We have to subtract off 2 radii. So I'm going to try to do the math at the board. We'll see how far I get. But basically we'd have minus 2 RB over RG1. So what that does for us is allow us to solve for RG1, because obviously RB is just 30 millimeter. And if we solve for RG1, let's see, we'll end up with, well, I guess I better do it at the board and make sure I didn't make a mistake there too in the algebra. Well, that's okay. So V4 over V1, those are just numbers. Let's make it that way. So V4 is 240 pi over V1 is 540 pi. Obviously the 2 pi's cancel. That's nice. We could subtract a factor of 10 from the 2 if we'd like. And then just do the algebra. So 24 over 54, well, 1 minus that would be equal to 2 times 30 millimeter over RG1. If we take 54 over 54, take 24 away, then that's 30 over 54. Let's see, yeah. So then if we divide by 2, well, we could cancel the 30s across if we wanted to. And then from this, RG1 would be equal to, we'll just invert and multiply. Well, no, multiply across actually. RG1 would be 2 times 504. So RG1 would have to be 108 millimeters. I was consistent with the units, so I didn't really need to write them down. Now I calculated 54 millimeters because of the factor of 2 in my solution. So now we should be able to calculate the angular velocity of B, for example, right here. And that's one of the things they asked for. Angular velocity would be V1, which we know is 540 pi millimeters per second. RG1, I believe, is 108 millimeters, despite what I said in my solution. And so before, I got 10 pi, but I'll get half of that now because my denominator is twice as big, so it should be 5 pi, I believe. Yeah, that makes sense. And these would be radians per second as the angular speed. I did convert that into RPM, and when I converted it, using similar conversion factors to what we did there, I found that the angular speed had to be 300 RPM, but now, instead of going from 10 pi to RPM, I'm going from 5 pi to RPM. I should get 150 RPM. So at this point, that's my answer, despite my mistake in my solution. And that'll be the same angular speed for the other bodies as well. And then we need, what else? The angular speed of the spider. So what I did there is I said, well, that spider really has a point also on body B. It's right here. If I knew the velocity of that point, well, then I would know the velocity of that point on the spider, and that should give me the angular speed, because then I just have 2 radii to get out to that point. So basically the velocity of B is the angular speed of B times what? Well, the center pivot, wherever it's at, let's just draw it down here somewhere. Let's call it G1. RG1 is still here, right? From here to here is the same from here to here. What we need now is the distance from here to here. So that would be whatever RG1 was minus one of the radii. Now I've got RB over 2. I think I was using diameter instead of radius. Let's make sure that all my numbers make sense. Yeah, the radius of the gears is 30 millimeter. I was confused in using them as diameter. So I think this will be different too, but let's try it. So the angular speed of B, we know, I'd rather use it in radians per second, we'll do that. And we need the distance, RG1. I shouldn't have erased that graphic I had here. It looks something like this. Remember where this is point G1, this is point 1, and this is point 4. Really, the center of B is right here, so that's the velocity I'd like to find. So, all I need is RG1, which is that distance, which I now know I may have, here it is, 108 millimeter. And I need to subtract off the radius. Now in my solution, I subtracted off half of the radius. So let's again do the math at the board. So minus the radius of B. And that would be 5 pi times RG1 was 108 millimeters, although I've got 54 here, minus 30 millimeters, okay, for RB. And that's different enough. Let's see, I guess, well, let's see, if we pull a factor of 2 in there, actually this will work out. My mistakes canceled out. And I believe this will come out to a velocity of 390 pi millimeters per second. You might want to double check. But I used 10 pi times 54 less 30 over 2. So that factor of 2 from the 10, we pull it in, it's the same thing. So I think that will work. Okay. And then the velocity of B is also a point on the spider. It's not just a point on the gear B, it's also a point on the spider. So now the spider is certainly spinning about this point, not G1. So this point has a distance of 2 times the radii, or if you like, the radius out to E minus the radius of A, or 2 times the radius, 60 millimeter in other words. And I used RA over 2, so this number is messed up as well. Anyway, so VB would be omega B times the distance from here to here. We'll just use 2 times the radii because that's what it is. So 2 times, well, let's just do it this way. Radius of A plus radius of B, which are the same. And then that would be, let's see, angular speed was 5 pi radians per second. And let's see, RA and RB are both 30 millimeters, so that's 60 millimeter. So from here, 6 5s are 30, so this must be 300 pi. And those are millimeters per second, but I think I'm running out of camera space. Let's see. Wait a second, what am I doing? I tried to use omega B, no, that's fine. Yeah, that's okay, we're all right. Oh, no, what am I doing? This would be the angular speed of the spider. I'm not calculating the, there we go. Huh. It's hard to work through my solution and try to figure out what I did that would be different and see if I can come up with numbers. So like I said, I wanted to talk about the velocity of B on the spider. That's why I'm using the distance RA plus RB. There we go. So if we then solve for the angular speed of the spider, which is what we wanted, it would be the velocity of point B divided by RA plus RB. There we go. And so the angular speed of the spider would be 390 pi millimeters per second, all divided by 60 millimeters. Now that we should be able to do in our heads. Let's see. That is not what I had before, because in my denominator I had 90 minus 30 over 2. I should have simply had 90 minus 30. And it came out nice and round. So my number is going to be different now, and I need to correct my solution. We can cancel this. 39 by 6, well 36 divided by 6 evenly, so that'd be 6 point, 9 over 6? No, not, yeah, 6 and a half. So 6 and a half pi, whatever that is. And as far as numbers, we'll put it in your calculator. It's roughly 3 times 6 and a half. So roughly what, 18, 19 and a half or so? and they would be radians per second. So there's my updated answer. Before I converted it, I had 5.2 pi radians per second, converted it into RPM, got 156 RPM, so this would be faster than 156 RPM. But there it is. The principles are right. I still may have made a mistake at the board, but I think this is correct.